Swayam Prabha. Digital India. Educated India.
So, hello everyone. So, we will continue with ring spinning. Now, the traverse motion in ring spinning, that is bobbin formation, is very important, and this traverse motion we get from the cam device. So, let us first try to understand basics about the cam devices, because it is a general application. So, before we go to the specialized application in ring spinning. So, first try to understand briefly about the cam. So, cam mechanics is that the cam has got basically three components. One is the cam, this is the cam, okay, and then follower which transmits motion, the rotational motion, generally rotational motion of cam to a linear motion, and there will be slider through which the follower is actually been controlled. Okay. Now, there are different terms. First, let us try to understand the terms commonly used in the cam. So, rise is a term, is it is when the follower is moving away from the cam center. So, that here suppose this is the cam center and here is the follower, this is the follower. Now, if it is rotating in anti-clockwise direction, that means the follower will be moving away from the center. So, when it is coming here, so it will be moving upward. So, that central distance from the follower to the cam center is increasing, that is it is called rise. So, here when it is moving anti-clockwise, this during this path when the cam follower will be moving, so that will be called rise. That means, from the center the cam follower is moving away. Then dwell will be some place if we need. So, there will be one place where the cam profile is actually circular in nature. So, this is the zone where even if cam rotates, the follower will not move, okay, linear movement will not be there. So, at this period follower is stationary, that is called dwell. And return means this, it is opposite to the rise, when the follower moves back towards the cam center. So, if it is moving in anti-clockwise direction, then this is the rise, here it will be when it is moved in this fashion. So, from this maximum point it is coming to the towards the cam center. So, that is why it is called a return. Now, stroke, okay, or a total follower travel, or it is called throw, is the greatest distance through which the follower moves. So, that is basically difference between the from the cam center to lowest radius to maximum distance, lowest distance to maximum distance, that difference is called stroke or throw. And displacement is the position of the follower for a specific 0 or rest position in relation to the time or rotary angle. That means, suppose this is the stationary initial position, okay, and this is the 0 position, and if it suppose it moves with certain angle theta, So, that distance travelled is called displacement. Velocity is the speed with which the cam moves the follower. So, the velocity will keep on changing, we will discuss in detail. Now, acceleration is the rate of change of the follower velocity. We are not talking about the velocity of or rotational velocity of the cam, RPM of cam, but we are talking about the follower. The velocity and acceleration is actually in terms of followers velocity, followers acceleration, and jerk is the rate of change of followers acceleration. Rate of change of velocity is, we know that acceleration, and rate of change of acceleration is the jerk. So, this we can plot the jerk based on the cam profile. Now, a follower displacement curve, this is the follower displacement diagram. It is a graph showing the displacement of the follower plotted as a function of time. Okay. So, in x axis there may be time, or if the cam, generally cam rotates, cam shaft rotates in constant RPM, constant speed. So, in x axis we can also express in terms of angle of displacement, angle of movement. Okay. So, since the cam usually rotates at a constant angular velocity, so that time axis can be considered as theta axis. So, in that x axis we can, instead of time we can express in terms of theta, and it is plotted from 0 degree to 360 degree, that is full rotation, full one complete rotation we plot. The follower displacement diagram that determines the shape of the cam. So, this is the follower displacement diagram, okay. And here this will actually determine the shape of the curve. So, we can have the follower displacement with certain requirement, and from there we can get the cam profile. Now, this is the cam profile. Here in this cam diagram we can see that we have different points. This is the cam, okay, light blue color, it is a cam profile here. Now, we have the term follower we have discussed, and this one is the cam profile, and follower travel we will discuss, pitch circle or pitch curve, this is a pitch curve, prime circle and base circle. So, these are the basic terms. Let us discuss this term, try to understand the meaning of these terms. Now, cam profile, you can see this is the cam profile, is the actual working surface contour of the cam. So, if we have, this is a cam. So, this profile is known as the cam profile. Okay. It is the surface contact with the knife edge. So, knife edge follower if it is there, that is the surface contact point, or roller surface or flat surface. So, if it is roller follower, so that is the actual surface contact point, that profile is called cam profile. Now, here this is a, you can have the cam profile also, this one is the cam profile, actual cam profile. Now, the base circle, the dark blue color is the base circle. What is that? It is the smallest circle drawn on the cam profile from the radial cam center. So, this is the radial, the cam center, radial cam center is that, and with the cam profile, the smallest radius we can draw. So, we can draw many such circle. So, this with this profile we can draw circle, with this profile, different profile we can draw different circles, but the minimum smallest circle is known as the base circle. So, obviously, the cam size is dependent on the established size of the base circle. So, we can have same follower movement, same displacement, okay, same stroke with different base circle, and that basically base circle is actually it shows the size of the cam. So, for same stroke we can have different size, that depends on the different size of the cam, but that depends on the base circle. If we want a smaller cam, so base circle should be smaller. So, this is base circle. Now, trace point is the point, you can see the trace point, this is the point on the follower located at the knife edge roller center. So, that is the trace point where follower and spherical face center. So, in case of knife edge, the trace point will be the cam profile, but in case of spherical or roller center, the center of the roller's movement will be the trace point. So, here you can see this is the trace point. Okay. Pitch curve or pitch profile is the path of the trace point. So, this where we can get a trace point from different locations, and the pitch curve or pitch profile is the path, entire path is of the trace point is the pitch curve. In cam layout, the curve is often determined first. Okay, that we have to first determine the pitch curve, and the cam profile, okay, is then established depending on the size, of the follower. Okay. For the elementary knife edged follower, the pitch curve and cam profile are same. So, if the cam profile is flat, okay, knife edge follower, that means the pitch curve, okay, pitch curve and cam profile will be same as I have mentioned, and for roller type it will be little bit different. It will be basically that the roller radius has to be added, and prime circle, we can see prime circle is the smallest circle that is drawn on the pitch curve from the center. It is the smallest, it is similar to the base circle, that means smallest circle drawn from with the pitch curve. So, pitch curve will be also be pitch circle will also be following the cam profile. So, for cam profile, from the cam profile we get the base circle, and from the pitch circle we get the pitch curve, we get the pitch circle. Okay. The pressure angle, you can see the pressure angle, this is the pressure angle. Pressure angle is the angle at any point, we can have pressure angle at any point, okay, between the normal to the pitch curve. So, pitch curve is the, then we draw the normal and the direction towards the direction of the follower motion. So, that angle is called pressure angle. This angle is important in cam design because it represents the stiffness of the cam profile. So, if the stiffness of the cam profile is very high, then it will have jerk. So, too large it affect the smooth running of the. So, we cannot have very high pitch angle. So, that we have to see, and we can reduce that pitch angle by adjusting the base circle. So, that is also important. Now, pitch point is that point on which pitch curve having the largest pressure angle. So, that here is the pitch point. Okay, these are the basics of the cam nomenclature. Now, we will come back to the spinning machine ring frame. In ring frame, cup formation, mainly three parts are there. What are this part? One is base, okay, carved base, where we want to store larger quantity of material, okay, to have higher more cup size, keeping all other parameters same, the diameter of bobbin and height of bobbin same, we can have higher quantity of material. In center there is cylindrical one, and at the tip top portion it is a conical. This conical formation is there throughout the bobbin. So, that will actually require, that is required for easy unwinding, the nose unwinding from the top at very high speed unwinding is required. So, this type of conical formation at the top always should be there. So, three parts: A, the lower carved base, okay, this is A, here actually bottom we have shown, and Z, middle cylindrical base part, and S is the top conical shape. This is S, Z, and bobbin may be in plastic or cardboard. Now, we left free in from the tip and from the bottom, okay. Slightly taper to adapt the to the spindle. Spindle is little bit tapered, okay, for because we need tapered spindle maybe for the dynamic stability. So, it is sometimes slightly tapered, it is not purely cylindrical as it is shown here, and here what happened, the individual layers are superimposed. So, here superimposition are there, mainly two types of winding, one is main winding and that other is cross winding. When the ring rail moves upward, it moves at slow motion, but with a accelerating, slow and accelerating motion. When it moves upward, that time majority of the major quantity of material will be winding on the cup. This is called main winding, and while moving downward it moves at faster speed and with the retarding. So, it actually started with faster speed than the upward motion. So, here it is cross winding. Cross winding is required just to bind. So, this is called binding layer also. This is the winding layer and binding layer. So, this is required to have to prevent the sloughing off during high speed unwinding. So, if the angle of winds both in main and cross winding are same, then the things will be that there will be a upward pull and that will result a bunch of yarns coming together. So, that is just to prevent that, this system is adopted. Now, you can see during upward motion when the ring rail is moving slowly. So, majority of the yarns it is almost parallel. Okay. They are being wound during the, this is called winding layer. Okay. And while coming down, this is shown in black color. So, that is actually it is a, the angle of wind will be larger. Okay, here. So, that will have the binding effect. So, main winding, this is the, these are the main winding during the slow upward motion of the ring rail. Primary yarn take up, majority of yarn is wound on during this motion. During slow rise of ring rail, main winding takes place, and cross winding, which is shown in the black color, dark color. So, this is binding of take off layer. So, that main layer is actually bound by this cross winding during rapid descent of the ring rail. And what happens? It isolates itself from the main winding layer. So, if the angle for both main winding and cross winding are same, they are not being isolated. So, as I have mentioned, the yarn sloughing off may take place. Also, parallel winding sometimes takes place like winding. So, that is not for short staple spinning, for like jute or flax spinning, where we need different types of yarn package or roving package. This type of with a flange, where this type of flange, this is the winding. Here we can have parallel winding, no cross winding or no main winding. So, this type of winding, but here the thing is that we have to unwind from the surface, it is called surface unwinding, and here as in the cone winding we will see, we from the top it is called nose unwinding. So, that is different aspect here, simple mechanism, but problem in unwinding. So, problem here we cannot have very fast unwinding, very high speed unwinding is not possible, because here the package, the ring bobbin, ring cop, it does not rotate, it is stationary. Only thing is the yarn is being pulled from the top. So, without movement of the, without any rotational motion or without any motion of the ring cop becomes it is stationary, it remains stationary, but yarn is unwinding. But here in other case parallel winding, we have to rotate the this ring this package by yarn pull, and that the this load heavy package we have to rotate. So, we need very high inertia or torque is required, and due to the high inertia, as in case of breakage, so this will keep on rotating. So, that there may need to be have one brake arrangement. So, this is complex, problem of unwinding is there. So, this is not in used. So, parallel winding is not in used, where main winding and cross winding type winding is used in normal ring spinning. The winding process. So, point of lay constantly moves up. So, it is constantly moving up due to the ring rail motion, ring rail moving upward. So, point first at this laying point, then next layer. So, that is important. Here one thing we have to remember, that the next layer has to be put on the just above this coil during the winding, above the previous coil. There should not be gap. This may be achieved by gradual rise in either gradual rise in ring rail or gradual lowering in spindle rail. So, to lower the spindle rail we need the complex motion, okay, that it will total spindle rail is driving, it's the driven by the drive arrangement. So, that will give complexity. So, this lowering the spindle rail is or lowering that is moving the spindle rail up and down is not done. So, gradual rise or lowering the ring rail is done. So, during the winding process gradual rise in the ring rail is adopted. So, spindle rail movement is not in use. So, there will be two types of movements, one is continuous upward motion, okay. Another motion is the gradual rise in small steps. So, what is that? So, suppose it starts from the base. So, this is movement and it is coming down in next, and next layer will start little bit above that. So, there will be gradual upward motion in this fashion. So, the winding takes place. Balloon control ring and thread guide. So, here we will have a balloon control ring. So, ring rail will be somewhere here. So, this is ring rail, suppose this is ring rail, balloon control ring will be here, BC ring, balloon control ring, and this is ring rail, and here at the top there will be lappet guide. Okay. So, this the thread guide. So, these three they have the similar movement, same movement will be there, while when the ring rail is moving up, balloon control will also move up, and thread guide will also move up, but their movement, the extent of movement is different to reduce the tension variation. So, balloon control ring has to move to reduce the tension variation, and but the shorter stroke. So, if it moves at the larger stroke, so balloon control ring will be movement will be at the short distance. Now, if I draw the movement of ring rail, this is the movement of ring rail in this fashion. Now, balloon control ring, if we try to see, balloon control ring will be moving in the same fashion, but with the lower extent because of the space constraint, and the thread guide will also move, but it will move further lower extent. So, due to the space constraint, but it is required to compensate to reduce the tension variation. This type of movement are required. Okay. But shorter stroke, so traverse and lift are shorter stroke, and the winding layer slow with increasing upward speed. So, winding speed is, it is winding layer, it is slow. Slow means it slowly, because we need to store more material. So, that is why the coil number of coil per unit length should be high. So, that is why we move it at slow speed, but increasing speed. So, increasing speed is required because what we want, let me draw, this is a bobbin and initial at the bottom. So, at the bottom the speed is slow, but while we are moving upward, so speed is increasing. So, in this fashion. So, what happened from the very first layer, there will be large quantity of material at the base, but material content will gradually reduce as we are going upward within the stroke. So, we can see here from the first layer also, although the extent is very small, from the first layer, this is the bare bobbin, from the first layer we have conical formation. So, this is due to the base is due to the slow motion, and as it is moving faster. So, this will be at the fastest speed. So, there will be less quantity of material. So, effectively if we see, if we try to draw the wrap, these are slow speed in this fashion. So, here at the base, again let me draw, at the base it is a slow motion. So, number of coil per unit length is high. Now, in this fashion. So, here at the base content will be more. So, it will form the taper from the beginning. Quickly with decreasing speed downward. So, downward again it is moving quickly, but it is decreasing. That means, at the base again we are having larger quantity of material. So, both winding layer and cross layer, they are ensuring that from the beginning there will be a taper formation, okay, taper formation, and this individual tapers are overlapped. So, that I will discuss. So, the speed, the length ratio is approximately 2:1 in winding layer and while moving upward and downward. Total length should not be more than 5 meters, it should not be too much. Now, builder motion, this is the builder motion. Now, due to the cam, here the cam, as we have discussed, due to this cam, the ring rail moves up and down. Okay. Each time lever moves down, this lever moves down, this is the lever, and here if we remove the cam, because this is the rope, okay, and here we have one pulley, and with the same shaft, this pulley is the pulley B is the ring rail pulley, and pulley C is the balloon control ring pulley or the lappet pulley. So, total this ring rail is hanging on this rope, and if there is no restriction, suppose there is no cam, in absence of cam, this total lever will simply move upward because of the load, and there will be free fall of the ring rail. So, that ring rail free fall is restricted by the cam. So, this follower O is by default will be in contact with the, it will always put the upward force on the cam. Cam is restricting, and the rotation of cam, what it does, it is only pushing the lever downward, pushing this follower O downward, so that lever moves downward, and that is downward from the during the stroke from the lower radius to higher radius. So, during this time, as per this diagram type of cam where it is moving anti-clockwise, So, during this movement it is moving downward, at this point it is moving downward, okay, and when it further it is moving. So, it is coming to the lower diameter. So, this is moving downward, it is going to maximum radius, and from during this time it is moving upward. So, that is due to the contact. So, this is the motion and it presses the catch. Here the catch is there, which will be pressed, okay. And what will happen? This ratchet will rotate for say one tooth or half tooth. To release the ratchet, will S thus rotates the drum. This drum will be rotated and it will wind some small quantity of rope, and which will result permanent shift of the ring rail. So, as we have, this is one, next layer will start little bit above, in this fashion it will move, okay. Now, short length of chain is wound on T, which will ensure the permanent shift, slight rise in position of the ring rail. Ring rail will be moved little bit higher. So, gradual shifting upward will be there, and balloon control ring and lappet F also moves up and down along with the ring rail. Now, here the total traverse length, this is the traverse length. This traverse length is controlled by the size of cam, position of this cam, length of the lever. So, all these parameters controls the traverse length. And shorter distance. So, if we have suppose finer yarn, so where we need fine small lift off, okay, slow, and for coarser yarn we need to move fast, permanent shifting should be fast. So, that is done by the size of the ratchet wheel. Now, you can see here this is a curved base, curved shape base, and for higher quantity of yarn in the package, and this is done by this projection N. So, by auxiliary mechanism, that deflector N is there, and disc A carries this N projected beyond the periphery of the disc A, and at start N deflects the chain. So, at the starting point position initial, the N is positioned in such a fashion, it deflects the chain, and rising lever H, this rising of the lever, this lever whatever it is rising, that is not fully transferred to the ring rail. That means, ring rail will move in a shorter span, shorter length, moves a shorter distance, okay, and the volume per layer will be increased. In the further course, this N will come out of this action, and disc A rotates slowly in steps, thereby chain is in contact with disc only, not on N. This N will come out of this chain. So, chain will contact only with the disc. So, then there will be a normal movement. Now, so before that let us see the animation of this building motion. So, here we will see how this cam motion gets transmitted to the ring rail motion. Okay. So, here is the animation for building motion of ring spinning. Now, let us see here animation. Now, we can see the cam, this is the cam rotates in the anti-clockwise direction, and using the cam's motion, so it pushes this follower, okay, follower, the lever, it is pushed downward, and that will actually the speed is actually the whatever the cam's profile, this through the rope, okay, through the rope, this the speed of the motion of the ring rail is changing, okay, and the ring rail has got, it is basically hanging on this simple on this rope, and it is the lever is pushed against this lever is pushed against this cam profile, and cam profile only presses downward. The upward movement of the lever is done by this mass of the ring rail, which is heavy ring rail is hanging, and depending on this shape of the cam, the traverse speed changes. So, that the traverse speed, that basically the traverse speed is that when it moves upward direction, okay, upward direction, that is basically it is called the winding layer. It moves slowly, but with the accelerating speed. So, at the base it is slowly and with the accelerating space, so that the tapering takes place, and when it moves downward it is a faster speed, okay, and that is called binding layer. So, winding layer and binding layer is done with the use of this cam profile, okay, and also there is a projection here, you can see the projection N, this projection N, this is basically to form the base of the bobbin, where a large quantity of material is to be stored at the base. So, this due to this the projection, the whatever deflection is there, that is absorbed, most of the deflection is absorbed by this projection. So, that the ring that is not getting reflected at the ring rail. So, ring rail motion will be less at this time, at the base, so that the larger quantity of material is stored here. So, here at the base, so when this projection comes into the action, so the base is formed. Okay. So, this is the overall animation. So, we will continue with this the understanding of the cam profile. Okay. So, now the base building, that is belly of the cork, okay, controlled by mechanism, that is projector mounted on the oscillating disc. It superimposes its motion on the basic motion derived from the cam profile. Now, we will get this type of belly. Now, after that what we are getting here, you can see there is a trapezoidal conical layers are there, and this trapezoidal conical layer is superimposed with the shifting, gradual shifting, and we will ultimately after certain time we will form a parallel layer, which will be the cylindrical middle portion. So, base of the cup is shown in the grey color. This is the base of the cup. Each of the winding coils laid during the formation of cylindrical portion is shown in separate different colors. So, they are actually forming the cylindrical layer. Binding coils are not shown. So, this is only the winding coils. The pitch of yarn coils P must be the same for achieving the proper shape of the coil. So, this pitch will be should be actually same. Uniform density of the package in the yarn. So, what is the pitch? So, that means distance between coil. To obtain maximum yarn content. Now, conicity of the cup greatly increases during the building of the base of the cup compared with the conicity of the plastic tube. So, plastic tube has little conicity, but the conicity we achieve, as I have discussed, due to the movement of the ring rail. During the upward motion of the ring rail, the yarn coil, the winding coil are wound with the decreasing diameter of the cup from the bottom to top. So, there is a conicity of the package, but this is not that great, right? But due to the motion we get the conicity of the, this is the first layer, second layer will be like this, third layer like this, fourth layer, fifth layer. After certain time we will see this will be approximately a parallelogram. So, large number of parallelogram will be formed, and finally, we will see this, after this we will have the cylindrical package. The lowest diameter of the coil ds is being the bare plastic tube. Maximum diameter of the yarn package or the yarn coil DL can be set about 0.9 to 0.95. So, it should be little bit less than the ring diameter. So, otherwise there will be problem in movement of the traveler. Now, the time required to wind one coil of yarn Ti, so for ith layer, is related to the package diameter and the yarn delivery rate K. So, package diameter is say di. So, this is the one coil and delivery rate is say K. So, pi d is the circumference of that particular coil, and delivery rate if it is K. So, that K, that is the Ti equal to pi di by K, which is the time required for that particular coil. Now, what happens, the diameter of the package changes. So, if this is the package size. So, ring rail moves from this point to this point. So, diameter keeps on changing. The pitch of the yarn coil is related with the velocity of ring rail. So, what will be the distance between two consecutive coils, that depends on the velocity of the that upward motion. We are only discussing the winding coil. Combining this above two equations. So, upward motion is equal to P equal to V T, that is pitch is P, V I is the upward motion of the rail, and T I, that is the pitch. So, one coil takes T I time, and if the motion is V I, so for that motion how much distance the for that time, one coil T I time, how much distance the ring rail will move up. So, so that next coil will be placed. So, this distance is the pitch. Okay. So, using these two equations, what we can get? Pitch equal to K V I d I, okay, and K is a constant. K, when K is not constant, K is a this one. K is a basically here K, if it is yarn delivery rate, if we try to, if we say delivery rate is constant, in that case K will be constant, the capital K will be constant, which is pi by K, that is K. And when if the yarn delivery rate is constant, we can have this relationship, pitch we can calculate. So, pitch is nothing but the this movement. Now, here from the profile of the cam for building yarn package. So, this is the profile. So, here we can calculate the pitch from the profile. So, profile is cam profile is important. So, for 1 degree rotation, per degree rotation, how much will be the movement, that we can calculate from the cam profile. The velocity of ring rail while rising, okay, increases from V1 to V2, V3. So, gradually it will increase, while the winding on the package with decreasing diameter D1, D2, D3. So, if we draw the package, this is the package and ring rail is at the base here, base of a traverse. So, when it is moving upward, so it is going decreasing diameter is there, decreasing bobbin diameter. So, velocity has to increase while moving upward to keep the pitch constant, pitch has to be kept constant. So, V2 will be related with the diameter. So, V2 equal to V1 at a certain point, and just above that point the V2 will be there. So, if we see there, this is the package at this point, if it is diameter is D1, at this point next layer diameter will be say D2. Okay. Now, here at this point speed is V1, okay. Here speed will be V2. So, if the diameter 2 is lower than that, so V2 will be higher than V1. So, we can see here. So, diameter 1 is more than diameter 2, more than diameter 3. Similarly, the V1 is less than V2 is less than V3. So, that means the speed will increase. So, that is achieved by the proper designing of the cam. So, velocity of the rail increases while rising and the displacement of the cam follower must be increasing for every angular rotation. So, that is there should be some acceleration, velocity should be increasing. So, rate of change of velocity we can control by proper designing of the cam. Now, we can see here from this curve. Now, this is the displacement profile from 0 degree to 360 degree. So, this is the increasing at 240 degree, that is a maximum displacement, and then it's that means it is moving upward slowly and then it takes up to 240 degree. So, two-third of movement as per this curve is used for the upward motion and 1/3 is required for downward motion, the fast descent. So, you can see the total yarn content will be 1:2. So, here the double yarn than the descent. Okay. So, that is the movement up and down. Now, velocity profile. So, from the cam, if we control, if we see the earlier equation, velocity of the ring rail we can plot to get that equation satisfied. So, this is the velocity profile. Okay. And that this we can always plot from the equation, from this equation we can get this plot, and the acceleration also we can calculate. If we want to calculate the acceleration, we can also calculate. So, acceleration you can see at the beginning the acceleration is high. So, gradually the acceleration is reducing towards, okay, and then after while descend it will be retarding. Okay. So, in this way the movement of the cam, velocity with the particular cam rotation and acceleration can be plotted, and we can, if we want to change this any one of this thing. So, we can change the cam profile. So, depending on our requirement we can change the cam profile. Now, what we will discuss the twist compensation in ring frame. It is very important. Let us try to understand how the twist get compensated in ring spinning. What happened in ring spinning, if we say the twist, what is twist in ring spinning? Normally we say the spindle speed by delivery rate, that is what we normally say, but in case of ring bobbin package this is not the case. Ns by Vd is not the twist applied on the yarn at the bobbin stage, ring bobbin stage. Twist in the ring spinning, twist is imparted not by the spindle, but by the traveller. Only. So, there one rotation of traveller imparts one twist in the yarn. So, effectively twist in bobbin, ring bobbin is traveller RPM by delivery speed. Okay. And here we will see the traveller speed, spindle speed is always constant, but traveller speed changes depending on the bobbin diameter, okay, ring bobbin diameter. So, the Vd equal to pi dB bobbin diameter into ns minus nt. This is the relationship that we all know. Now, here delivery speed in ring spinning constant, spindle speed is constant. Now, with the increase or decrease in bobbin diameter, the traveler speed changes, traveler RPM changes. Now, if we see only one stroke, only one traverse, if we see, this is the package. Now, here the ring rail is there and it is moving upward. So, diameter of bobbin is reducing from this point, say bottom to top, diameter of bobbin is reducing, and while moving upward and while moving downward, diameter of bobbin is constantly increasing, continuously it is increasing. So, this is the diameter of bobbin changes continuously within one layer, even during the winding. First it is a smaller diameter bobbin, then when its package is becoming full, it is a larger diameter. So, we will see the NT is continuously changing. So, this change in NT affects the twist, that means twist in the yarn package is continuously changing. So, that means if we try to use this yarn as such, then we will find the twist at different point or majorly there is significant difference in twist. So, this yarn will be actually effectively useless. Now, fortunately during the unwinding of the package, this twist gets compensated. Now, try to understand this aspect with examples. Now, this is the yarn that manufacturing process in ring spinning. Now, this is roving, that these are the delivery roller, feed roller here, lappet, balloon formation, ring, traveler, and total draft is delivery speed divided by feed roller speed, that we can get the total draft here, and twist here, twist at this package is N traveler RPM by delivery speed, and velocity of traveler pi d into traveler RPM. So, winding speed is spindle speed by delivery speed. So, these are the basic relationship. Now, each layer consists of main layer, cross layer, as we have already mentioned. Ring rail speed increases during upward motion and speed decreases during downward motion, and speed at the tip of each layer is higher than the base layer, both up and down. So, when this is one layer, so at the next layer, upward layer, the speed of the ring rail will be higher than the previous layer. Thus, material accumulates at the tip is lower, leading to conical shape. So, always the speed at the upper side is higher. This is true for upward movement and downward movement. So, upper side speed is higher, that means material accumulated at the lower portion is larger, as I have already explained. Now, for first layer, let us see the thickness at the bottom is B1. So, you can see this is the thickness at the bottom B1 at the first layer, and the speed is suppose in such a fashion, the speed at the top is double than that of bottom. So, thickness will at the tip will be half of B1. So, B1 by 2. If the speed at the bottom is half of the top, then first layer will have trapezoid shape, B1 at the bottom and B1 by 2 at the tip. This is the trapezoid. So, B1 B, so now here B1, next will be B2, third one will be B3, fourth layer will have B4. In that way it will continue. So, B1 is more than B2, is more than B3, in this so on, due to increase in bobbin diameter of the at the bottom, as it is increasing. So, due to that the thickness increase will be lower. At bottom the diameter increases continuously and it is continually narrowing trapezoid. So, trapezoid will be gradually narrowing down and eventually this will form a parallelogram. After certain time it will form parallelogram. So, initially in this form narrowing down and then this parallelogram will continue till the end, but at the tip we will always have this type of conical shape. Now, let us try to understand with an example. Now, here L is the delivery rate, pi dB and spindle RPM, and NT is the twist. NT is the RPM of traveler. Now, NT equal to spindle RPM. So, we can just rearrange this thing, L by pi dB bobbin diameter at any instant. Now, the observation is spindle speed is constant. As bobbin diameter increases, the traveler speed, bobbin diameter increases. So, traveler speed will also increase. Okay. Diameter continuously changes within the traverse and from start to bottom. So, it is continuously changing. That means, your NT is continuously changing. Okay. And let us take one example, spindle speed say 13,500, just random example we have taken, delivery speed 15 millimeter per minute. Okay. So, 15,000 millimeter per minute and the bobbin shape is like that. At the base of the traverse it is a 46 millimeter at particular instant and at the tip of the traverse it is a 25 millimeter diameter. D is changing. Now, here we can see the traveler speed with this data at the bottom is 13,392. That means, it is lower than the spindle speed. That means, it is actually we are reducing the twist with reference to spindle speed by this much RPM. So, what is that RPM? We will calculate. Similarly, at S position tip, the RPM of the traveler is this one 13,309. So, it is losing its twist by this much 15,000 by pi 25, pi multiplied 25, this much revolution, it is a losing with reference to the spindle speed. So, that missing turn with respect to the spindle speed at the bottom, we are missing is 103 RPM, 103.8 RPM at the bottom. This much RPM we are missing with reference to the spindle speed, and at the top we are missing by 191 RPM. So, that means that much twist we are missing with reference to the spindle speed. Now, let us convert it to twist. So, turns per meter, if we try to see, this is the actual theoretical turns per meter is traveler RPM by delivery speed, that is theoretical or actual transfer, actual in the bobbin, because this turns per meter we will not be able to get, because after unwinding we use this material. So, practical turns per meter we use in the industry, everywhere we use spindle speed by delivery speed, but this is the practical turns per minute, but actual turns per minute is traveler RPM by delivery speed. So, compensation of missing turn at top during unwinding. So, at the, if we see the unwinding of the cup ring bobbin, we do not unwind the ring bobbin from the surface like roving frame. In roving we draw from the surface where roving the supply package rotates. Here the supply package does not rotate, we draw from the top. Now, what happens while unwinding one layer, one coil, sorry not layer, one coil unwinding will add the twist by one twist. So, that is added on the twist whichever is there in the ring cup. So, that every coil unwinding will add one twist. So, that is the compensation. So, what is compensation? Now, missing turn at top is 191 and the speed was 15. So, the total turns per meter which was missing with reference to the spindle is 12.73 twist turns per meter. Now, during the unwinding, the twist is added. Okay. So, per meter how much twist is added? We can see this is pi into 25 was the at the top. So, at top 25 was the diameter, pi 25 was the circumference, and while unwinding that circumference we are adding one twist, that means per meter the twist added will be 12.73. Then whichever we have missed due to the lower speed of the traveler, that is being compensated while unwinding of the same coil unwinding we are getting. So, this can be calculated at any diameter and we will see the same amount, whatever we have missed, same amount is added. Now, for the base we can see turns per meter. So, this is already we have discussed. Now, transfer meter at the bottom. At the bottom we missed 103.8 rpm. So, transfer meter was missed by 6.92. Now, here whichever is added is that 1000 by pi 46, pi multiplied by 46, 6.92. That means effectively after unwinding we are gaining that much twist which we have missed due to the traveler lag. So, after unwinding we will get the twist which is equal to the practical twist, that is practical transfer the effective transfer transfer meter is always spindle speed by delivery speed, but it is always after unwinding, but before unwinding the twist will be traveler rpm by delivery rpm. Now, if we have one system where the package is unwound from the surface by like the roving, then the twist will be traveler rpm by delivery speed, but this is not done, this process is not adopted in case of ring bobbin. So, the nose top unwinding is carried out where twist compensation takes place. So, we have discussed, we have tried to understand the cam profile, how the tapering takes place and how twist compensation takes place. Okay. And we will stop here. Next session we will try to understand few numericals related to ring frame. Thank you.